Hey there, welcome back to the Andromedoom devlogs, episode number 6. If you'd like to skip ahead to the content, please check the timestamps in the description below. In this episode, I'll be showing you how to implement a generic C# finite state machine and then apply that state machine to control our little alien invaders. So for the purposes of artificial intelligence. Now, if you've done computer science or electronics engineering, you'd be familiar with what a finite state machine is. But if not, what it basically is just an implementation of a flowchart, boxes and arrows. And in this instance, what a box represents is a state, which means what is this object doing, and the arrows represent transition, means what is this object going to do next. Finite state machines give us a way of creating very complicated behavior that is modular, compartmentalized, and easily extendable. Let's head on over to the screen. Now, this is where we left off in the last episode. We just established the projectile instantiation and taking damage. So we've got our little alien character here as a separate scene. It has its own little Space Invaders mesh and a box collision shape underneath it, with the empty alien script attached to it. I'm going to make one little change here. Now, this collision object, that is the kinematic body, is on the alien layer, and its mask, what we want it to collide with, we're going to deselect projectiles player. And that's because the projectiles themselves are responsible for colliding with objects that are destructible and then calling their take damage functions. So as this object moves, it doesn't really care if it bumps into projectiles. The projectiles will take care of that for us. Let's verify this. Yep, it still works. And so one other thing, on our level, what we have are the walls, and we want our alien to bounce off these invisible walls. Now, this static body layer is currently on the player layer, and they're not moving, so we'll just switch off the masks, but we'll create a new layer. Well, we'll rename the appropriate layer. So under project settings, general, layer names, 3D physics, we'll call this level bounds for layer number 6, and so we'll put this on layer number 6. And so when the alien moves, we want it to bounce off any buildings it collides into or any level bounds. However, we don't care if it bounces into aliens, projectiles, or the player. Let's head on over to the scripting. A finite state machine is an abstract structure. So if you ask 10 different people, how would you implement a finite state machine, you'll get 10 different answers, and all of them would be correct with their own design principles and intentions. So the way I'm implementing this is through composition. So the alien class would instantiate its own finite state machine. That state machine would have its own states, and those states would communicate directly with the script and control the behavior. Now, the first thing to do is to create the abstract data structures for the state machines. So let's create a new script here and call it patterns, and we'll define our own custom namespace. So Andromedoom tutorials is the solution folder name, so it's the default namespace in this project. I'm creating a sub namespace called patterns. Now, a state machine needs two things: the state machine class itself and the states, a generic state class. So let's try and work through the state machine first. Now, as I mentioned earlier, a finite state machine includes a bunch of states and transitions. However, transitions and the behavior of the states are implemented in the states themselves. The state machine is just responsible for organizing the states and maintaining the active state. Now, the way I did this is with a dictionary. So let's use C#'s inbuilt dictionary, and we'll also be using generics with this, as we'll discuss later. So what we're doing is creating a dictionary with a string key and a state value, which means we can pass a string, which is the name of the state, into this dictionary and output a state class. And always make sure to initialize your dictionaries. And I've given it a protected keyword, that way you can build finite state machines that are built on top of this generic finite state machine class and override this function. The state machine has an active state, that's what state is activated at the moment. Now remember earlier I mentioned that this is implemented through composition, which means this state machine needs a reference to any node that constructs one. Now we'll call this node for now. Now we'll assign the type of this node to node for now, but I'll come back to this in a second. Now anytime you build a custom class that does not inherit from a built-in type in Godot, you should define an empty constructor for reasons that I am not sure. But just to be defensive. So here's our empty constructor. But the constructor we want to be using is this one here, where when a node, like alien for example, so let's say using Andromedoom tutorials patterns, and in our alien script we create a private finite state machine FSM is equal to new finite state machine. Well, no, we cannot initialize it here. We initialize it on the ready function. And we pass in this. And so now this alien script creates a new finite state machine, and this state machine has a reference to the alien that called it. So we set node to the user parameter. Now let's have a think about our states. What we're trying to do with this state machine is control this alien class. Now the alien moves on its process and its physics process functions. And so the end goal is to define some functionality under each separate state that would execute on these functions. So let's work on the state class for now. And here we'll pass a public node. This is the same node that's passed here, so that way each state has a reference to the node that uses the state machine. And so each state will have its own process function, which is overridable, and this process function also takes in the delta parameter, because our alien class, which derives from destructible, which we wrote in the previous video, but ultimately the alien itself is a kinematic body. Now the problem is, when we're passing a node here, the node does not have a functionality to move and collide like a kinematic body. Kinematic body derives from node, but the implementations for all those functions for moving an object around come from kinematic body. So we could do something like this: public kinematic body node, and change it here as well. However, then we can only use these state machines with kinematic bodies. So the way to fix this is to actually use generics. C# syntax is in angle brackets T for type. And what this type represents is the type of node that uses the state machine. So we can change this to T, and here we can change all these to T. Now the finite state machine can be implemented by any class of object. Now depending on how you implement state machines, the controlling behavior can vary. The way I've done this is such that the individual states are responsible for moving themselves to the next state. And to do this, we need a reference to the state machine that calls them. Now the state machine needs a few functions. So the most important one is the add function, which adds a state to the state machine. So here we take the states dictionary and we call the add method on the dictionary. And the string, well, we pass the name and we pass the state. Before that, our states need a reference to the node and the state machine. Cool, that's our add method. Now we've added states, now we need to worry about transitions, which are the arrows on the flowchart. So, our transitions only need to execute when the current state changes. So what we actually need to implement is a method for changing the state. And so to update the state of the state machine, we pass it the string, which is the name of the state, and is also the key in the states dictionary. And what we do here is we set the current state equal to the state's new state. Now what about the transitions? Well, on the state class, each state should have its own functions for entering and exiting. So when we update the state, we should call the exit function on the current state, change the state, and then on the current state, call the enter function. So whatever the state was before, we call its own exit function. Then we update the state on the state machine, and then this new state, we call its enter function. Now when the state machine is initialized, there's no initial state. So we got to be a bit defensive here and say, if current state is not null, and here we'll create a function that just returns the current active state in the machine. Alright, and that's basically the blueprint for a state machine. What you do now is then create new states that inherit from this class, and these states control the functionality of your object. So let's apply this to our alien script. Now, got an alien with its own state machine. We need to give this a type. Type of alien. That way, when we define member variables here, like for example, export private float, movement speed, something like that. Say half a unit every second. We have access to this field in the state machine. Now here we define our new states. So for example, in Space Invaders, the aliens move, they drop, they turn. So let's try and implement those movements. So we'll call this moving, and inherits from the state class the type alien. Okay. Now what do we want to happen when we're moving? Well, let's overwrite the physics process and move the alien. And to do that, all we do is select the node. Now remember what the node is. The node is the reference to the alien part that the state has. And we'll call the move and collide function on it. And to move forward, remember it's the basis z vector on the node, on your object. So node transform dot basis dot z, and we'll multiply it by delta, and the node's movement speed. So it does define the physics process, but how does the alien know to do it? So on our state machine, let's create two new methods. and we'll call it execute state process delta. And all this does is it calls the process function on the current state. And here we'll do the same. Physics. And we execute the physics process. And so on the alien, which is our kinematic body here, during the physics process, all the alien needs to do is call the execute physics function on its finite state machine. And here we need to pass in delta. And on our ready function, we built a new state machine, but we've got to assign new states and give them names. So we've only defined one, which is moving at the moment. So let's go init machine, add, we'll give it a name called moving, and the type is a new class moving. So let's test this and pray that nothing breaks. Small bug. We need to set an initial state. So set current state to moving. Okay, let's test this. And as you can see, it's moving, though in the wrong direction. And that's because the forward basis vector is in that direction. So let's have a look at our spatial node here. Yeah, so what we'll do is just rotate this mesh and we'll adjust our collision shapes. Good practice not to ever adjust the transform on your collision shapes, just change the box shape. And yeah, leave the transform untouched. There we go, much better. Now how do we change states? Let's say after 2 seconds of moving, we want it to start dropping. So let's keep track of time. So lapse time, and then on our enter function, let's override the enter function there. And here we'll just set our elapsed time back to 0. So every time you go from one state back to the moving state, this enter function is called and the elapsed time is reset to 0. And here we check to see. First thing you do is increment the elapsed time by delta. And if elapsed time is greater than, let's export another field. And we'll say move time, move duration, and we'll say 1 second. Node dot move duration. We will say finite state machine set current state to dropping. However, we have not implemented the dropping state, so let's do that. And it's largely the same functionality, so an alternative way of doing this would be to call dropping, inherit from moving, and then what we change is this parameter here, so some string as a member variable, and also this movement here, and also this vector here. But I'll just keep it this way as copy and paste for now, because the functionality can be a bit more complicated. So we're moving in the negative y basis. Now because these aliens never bank, in other words, their up vector is always aligned with the global up, the global vector that points towards the zenith. It doesn't actually matter in this case. Okay, let's test this. And again, we gotta add the state. Dot add dropping, new dropping. There you go, drops for a second, then he goes again, drops for a second. How about that? And we should change this private float, drop duration. We'll make him drop for half a second. Alright, let's make the alien turn. And this one comes back to our linear algebra, which can be very frustrating. Let's say turning. Again, inherit from state of the type alien. So how do we turn? Well, when we enter the state, the alien is already facing in a direction. The direction it's facing is the basis z vector. And now we want it to change direction to a random location in the xz plane. So let's store some member variables. Private vector 3, call this new direction. And then on the enter method, that is, when we first call when the state machine changes to the turning state, we'll update the value of the new direction vector. So let's initialize this to 0. And we'll give the x and z components random values. We do this with the random range function, which is on the GD singleton. Actually, I will use using static GD because you use it a lot. Godot .gd. Cool. And we'll call rand range. Now, unfortunately, the C# implementation takes double, so you'll have to cast it to a float. But basically, it'll be from -1 to 1. So it's either left or right. Completely to the left, completely to the right. Cast the double to a float. And similarly, we'll update the z direction. Now, is that it? Well, no. Now, the way we change the direction the alien is looking at is using the lookAt function, which is attached to kinematic bodies. Now, there's two issues here. One, lookAt takes a global position, not a relative one. And two, it actually aligns along it actually points the negative z basis towards the direction you're assigning, not the positive z. So what I'm doing here might appear a bit cryptic at first, but try and draw an image based on my previous videos discussing local and global coordinates. So our new direction, now at the moment, this is some value between -1 and 1 in the x, some value between -1 and 1 in the z, and 0 in the y. So it's at the origin and it's pointing somewhere along the xz plane. Now what we need is to figure out where the alien is and then move this vector towards it. So what you do is you take the origin of the alien, so node, but you don't want the local transform, which is relative to a parent. You actually want the global transform because the lookAt function works only in global coordinates. So global transform.origin, that's the location. Now remember how I mentioned earlier that lookAt points the negative z direction? So we're actually subtracting the new direction. And then we set node dot lookAt the new direction vector 3 dot up, and then we'll change the state. So we start moving in this new direction. All right, let's test this. First, let's add the new state. Turning. So once you finish turning, you go back to moving. Moving goes to dropping. Now dropping goes back to moving. So let's change this to turning. So the alien moves, drops, turns, moves, drops, turns, and so on. Drops, turns. Whoop. That is not meant to happen. Small boo-boo here. Make sure to set your new direction to 0, 0, 0 at the start of every time you turn, because the Y coordinate gets updated every time you turn, and you don't want that to change because it's a direction in XZ, so the Y component should always be 0. There you go. Now see that when it collides, it doesn't change direction. So what you can do here is when it's moving, check if there's a collision. So if collision is not equal to null, FSM.set current state to turning. So it generates a new direction. You can build this a little more sophisticated by finding out the incident direction and the reflected angle, which Godot can do for you. But we'll keep the example simple for now. There you go. Every time it collides, it generates a new random direction now. Okay, now the turning is a bit sharp, so we want to interpolate as we're moving. And we're going to do this with tweening. So, number of ways you can do this. Typically, to interpolate between two vectors, you'd want to spherically interpolate, which is the slope method. However, it is buggy, and I don't know if I think this is a problem with the C# slope method. You have to normalize both vectors, but even if you do normalize both vectors, there's no guarantee that the slope method will work. And if it works, it fails catastrophically. It completely terminates the program. So I don't use it, and I just use tween. So here, we'll create a new tween to this state, and we'll call it tween. Every time we enter, we'll initialize this tween. So tween is equal to new tween. And for the tweening engine to work, it needs to be in the scene tree. So initializing it isn't enough. It needs to execute on the physics, or I think it's the process step. So we'll add child. So we'll take the alien node, add child, tween. Cool. Now our tweening engine has a method called interpolate method. We're not going to be using property because that's very difficult. The problem with interpolate method is that it only takes one argument that is passed into the parameters of the method. The lookat function has two parameters. So we need to fix one of these by creating an auxiliary function on our alien class. Let's create a public void called look towards vector 3. So that's the direction. And what this does is it actually just calls the lookat function towards the direction. The vector3.up, it's fixed to the transform basis y. So this always rotates in the xz plane, this function here. And so what the tween engine would do is interpolate this method. Now the first argument we pass into this function is the reference to the object that contains the method. Animates the method of the object, which is actually, the node. And the second argument is the name of the method. So we'll say name of, in case we decide to rename it later. Node look towards. That's that new function we made. And our initial value, well, it's the original direction we were pointing at. So let's create a new private field so we don't keep constructing the vector at runtime. Here's what it is. It's basically the same as this, but instead of the new direction, it's the old basis. But we're subtracting, remember, because the lookout function points the negative z, not the positive z. So node global transform dot basis dot z. Cool. And so remember, the initial value is the old direction. The final value is the new direction. Duration. Let's export that. Turn duration. So let's make turning half a second node dot turn duration. And the last one is the transition types. And I find that circular works best. That's basically just the effect of the interpolation, how one value goes from to the other. There's like cool cheat sheets that shows how they work. If you want to see how they look, you can actually export this as its own private field, but we'll leave that for now. And to get the tween working, you start it. So we don't need this line anymore, and we certainly don't want to be changing the state straight off the bat. We want the animation to finish. So here in our, well, we can call it in the process function. I don't think physics matters in this case. We just check if the tween has finished. So it has an isActive method, which is just a bool. Is the tween doing anything at the moment, or have all its processes stopped? So if it's not active, first thing we should do is get rid of the tween, because we generate a new one each time we turn. And then we update the state back to moving. Ah yes, another boo-boo. I forgot to override the process function on the alien class. Execute state physics, no, execute state process. There we go. Fingers crossed it works this time. Would you look at that? Our alien is turning smoothly now. Now it's colliding with the building, so there we go. What I did in my main game is, if it's dropping, I make it change direction, but I make it bounce first. So I translate it up slightly and then make it change direction. So let's make the alien land height, let's say half a unit. And when it's dropping, we check to see if node dot transform dot origin dot y is less than node dot land height. If we do, we just return. So we just keep dropping, and if it's at 0, we set the state to landed. And when the alien's landed, let's just say that it does nothing. Now notice the alien follows the same trajectory each time, so it's a good idea to call the randomize method, which sets a new seed. Documentation says that it calls it at runtime, but from my experience, it really doesn't. So it's turning, it's moving. There we go. It decided to land at 0. Now the origin of this node is at the center, so either I change the logic to be offset, or I change the base, the mesh and the collision shape to be at the bottom there. But you get the idea. So that's the basics of state machine. So let's take a look at what we achieved here. Now that's a lot of lines of code for a relatively simple behavior. Now, if you didn't use a state machine, what you'd have to do is put all of these functions inside the physics process or the process methods. And because the order matters, it's actually almost unmaintainable. Now, the AI that we've built is very simple. It just drops, moves, turns, etc. And it lands if it's at a certain height. So, and even then, as simple as that is, it's on the borderline of how implementable it is. Just as a straightforward procedural program. So, I hope you took away how powerful finite state machines are in this context. Now, let's say, what if we wanted this alien to fire? So what you could do is in the patterns function, in the state method, you can actually pass here a state of type t and initialize it to null. Previous. Right? So what you do is you change this enter method to taking a parameter for previous, which we default to null, so we make it optional. And we pass the previous state into our enter method in the state machine. So update the setCurrent method with a previous state here. And you'd have to update your methods here. So state t previous. Let's just call a public void fire function here. And so here in the moving function, what you can do is pass in a bool, say already fired. Oops. I believe this initializes to false by default. We say if previous is equal to the state is, so here we'll create a public now when we enter, what the fired state would do is call the fire function and then change the state. So the new state is moving, and we'll pass the previous state, which is this. So if the previous state is fired, so if the alien has already fired, we set already fired to true. And we should update these values every time. Already fired. Paste in this line. Else set current state to fired. We should probably change this to firing, I think. That makes more sense. New firing. So let's test this out. I didn't implement the firing functionality because it'll take too long and it's outside the scope of this tutorial. But here you can see where the alien is firing incrementally. So he drops, he turns, he moves, he fires, keeps moving, drops, and so on. This is how you'd pass information about different states to each other and controlling the behavior based on what happened in the past. You can do, other methods, keeping track of, number of times it fired or generate behavior randomly, and I showed you a lot of these examples. But hopefully you come to see the power of state machines because it compartmentalizes different behaviors in different sections and makes building very complicated systems quite intuitive, extensible and maintainable. Now, one good practice here as well is to extract your classes. So you can click on this, for example, click the light bulb if you're using Visual Studio Code, and we can move the type to moving.cs. You'd want to organize this into folders, but keep in mind what this actually does is it makes the class partial. Alright, well, thank you for watching. I hope you took something away from this tutorial. Because this video is already quite long enough, I think I'll put off the devlog for the next episode. So tune in for that if you're curious. If you enjoyed this tutorial, please let me know in the comments. Any questions, suggestions, comments, leave them in that little box down below. And if you're enjoying this series, don't forget to hit like, subscribe, and hit the bell as well so you're notified when new ones come out. And I'll see you in the next one. Thanks very much, guys.